Our very last lesson here is the Doppler effect. So, man named after, that the effect is named after Christian Johann Doppler, an Austrian, published a paper in 1842 where he called attention to the fact that if a luminous body, like a star, is moving towards or away from the observer, the color or frequency, which you learn about a little bit later in Physics 30, the color or frequency of the star, which will appear different than the stationary star. So we look at the electromagnetic spectrum in Physics 30, which relates light back to waves. All right, so the fact that the color changes whether the star is moving towards or away from you was named the Doppler effect, which applies to all waves, including light and sound. So when a listener is in motion towards the source of sound, the pitch or frequency of the sound is higher than when the listener is at rest. So if we have a diagram here, we have the source of the sound is a fire truck. So if both of these people are at rest here, and so is the fire truck it's sitting, we will hear the same frequency as emitted from the fire truck both in front and behind it. Okay, now if the fire truck is moving, aka there is relative motion between the source of the sound and the receiver, so whether the source is moving or the receiver of the sound is moving, the frequency which is heard by the receiver will be different. Okay, so all of this is important here. Okay, so in our second example here, the fire truck is moving. So because this person is stationary, but the fire truck is moving towards her, she is going to hear a higher frequency sound rather than the person behind the fire truck. They will hear a lower frequency sound. So I like to think of it as the fire truck is moving, and so it would be emitting the same frequency, of course, but because it's moving, the space in between these waves has increased. Okay, so the frequency has changed. Now in this one, I think about it as like the frequency being pushed in the forward direction. All right. So there are two equations which are used to calculate the frequency of the wave, one is if the source is moving, and the other is if the receiver is moving. Again, if nobody is moving, the frequency heard will be the same. So when the source is at rest and the observer is moving is what we're looking at here. Source is at rest and the observer is moving. So Fs is the frequency from the source. F naught is the frequency received or heard by the observer. And V is the speed of the wave. V naught is the speed of the observer. So V naught is positive when they are moving towards the source. Okay, so when the observer is moving towards the fire truck, and V naught is negative when it is moving away from the source. So if this person was walking away from the stationary fire truck. When the source is moving and the observer is at rest, we have a very similar equation, just flipped here. And again, Vs is positive or negative depending on who's moving towards or away from. These equations, only one of them is on our periodic table, a formula sheet here. To get this one, we just switch the perspectives of the stationary and moving source or receiver. All right, if both the source and observer are moving relative to one another, we can combine these equations into one. Okay, so a few different examples here. A fire engine is roaring past you. So in this case, the source is moving at 15 meters per second while its 900 hertz siren is on. If the speed of sound in the air is 340 meters per second, what frequency do you hear as the engine comes towards you and goes away from you? So the speed of the source is 15 meters per second. The frequency of the source is 900 hertz. the velocity or speed, sorry, of sound is 340 meters per second. We need that reference point, and we're looking for the frequency from the observer. So we'll use the formula F naught is equal to Fs V minus S, Vs, sorry. Now, this is Vs here, because the source is moving towards the observer. So, subbing in, we get 900 hertz and 340 meters per second, all over 340 meters per second minus 15 meters per second. So calculating that out, we get 942 hertz. Now, if this fire truck is moving away from us, the sign of Vs changes. So we're going to get F naught is equal to Fs, V all over V plus Vs. So subbing in again, same thing, just a different sign. We end up with 862 hertz, so much different. Again, noting that the frequency increases when it's moving towards you and decreases as it is moving away from you relative to its original frequency being emitted. A car is traveling at 29 meters per second towards a stationary whistle with a frequency of 625 hertz. So the stationary whistle is the frequency of the source. So frequency of the source is 625 hertz. The car is the observer, and so it is traveling at 29 meters per second. The speed of sound is 337 meters per second. We are looking for the frequency as heard by the observer, the car. So in this case, we are using our other formula. So F naught equals Fs. And because we are moving towards the source, we will have V plus V naught all over V. So 625 hertz, 337 meters per second plus 29 meters per second all over 337 meters per second. We end up with 679 hertz that is heard by the observer. And our last one here, a whistle with a frequency of 2500 hertz is traveling south at 27 meters per second. You are traveling north towards the whistle at 15 meters per second. If the speed of sound is 341 meters per second, what frequency do you hear? Okay, so I'll just write out our formula initially here. So Fs V plus V naught, because the observer is moving towards the source, and V minus Vs because the source is moving towards the observer. So the signs were derived from the first two equations to use in our third equation here. Okay, so frequency of the source is 2500 hertz. The source is traveling at 27 meters per second. The observer is traveling at 15 meters per second, and the speed of sound is 341 meters per second. So just getting these three can be really tricky. Make sure you're reading the question and understanding who's the observer and who's the source. Okay, 2500, oopsie, another zero, hertz, 341 meters per second plus 15 meters per second, all over 341 meters per second minus 27 meters per second. Okay, we end up with 2,834 hertz. So it's much larger than our original frequency because both the source is moving towards the observer and the observer is moving towards the source. So we've amplified both of those increases, and we see a much more dramatic increase.